Homework last night was our navigation worksheet, and we had a request to do question number 5, so we'll do that. Just a couple quick little reminders before we do question number 5, however. When we're finding the relative velocity of something, and that's what we're doing in these navigation worksheets, is finding a relative velocity. Remember that we have to add vectors together. The example that I gave you yesterday when we started the lesson was you got an airplane moving at 800 kilometers per hour, and a baseball was thrown inside it at 100 kilometers per hour. What's the relative velocity? Well, we found that we discovered that we found the relative velocity by adding those two vectors together. And that was pretty easy to add them together, right? 800 plus 100 is 900, or 800 plus negative 100 is 700. Now we're doing relative velocity of questions in 2 dimensions as opposed to the 1 dimension with the baseball being thrown in the direction of the airplane's motion, or opposite to the direction of the airplane's motion. 2-dimensional problems. But in those 2-dimensional problems, we still have to add vectors together. We've spent several days now learning how to add vectors together. That's what you wrote your quiz on today, was adding vectors together. Okay, adding vectors together in a more difficult way than we have to deal with in the questions that we see here on our worksheet. So these ones, okay, if we remember a couple little tidbits of information, should actually be easier than what we've been doing over the last week or so. Remember that we have 2 types of vectors here, 2 kinds of vectors when we solve one of these relative motion navigation problems. We have solid line vectors and we have dotted line vectors. And I distinguish between the 2 by saying solid line vectors are vectors that contribute to the actual motion of the object. So an example of a solid line vector might be the wind speed, right? The wind contributes to the motion of the sailboat. It could be the river current. Okay, the river current contributes to the motion of the boat in the river. Okay, it could be which way I aim or which way I head. That's not where I end up going, but it contributes to where I actually end up going. Those are all solid line vectors. Now, dotted line vectors are resultant vectors. They're vectors that are the result of solid line vectors. Where do I actually end up going? Well, that's a result. Okay, that's a resultant vector. It's a dotted line vector. Where do I want to go? That's a dotted line vector. What's my velocity relative to the ground? What's my relative velocity? Those are all dotted line vectors, the result of solid line vectors. The result of, another word for solid line vectors would be contributing vectors, vectors that contribute to the resultant velocity. All right, let's do question number 5 now with all that information in mind here. 5 says, the captain of a ship aims his ship with a velocity of 25 meters per second directly north across a river whose current flows at 8 meters per second to the east. The river is 850 meters wide, and we want to find a couple of things. We're not going to worry right now about what we want to find. We're going to worry right now about what we have. So what do we have? We're aiming a ship across a river at 25 meters per second. Is that a solid line vector or a dotted line vector? Does that contribute to where we go, or is that where we go? Yep. That's going to contribute to where we go. So we're going to draw that as a solid line vector to the north. Now, we have a river current that's 8 meters per second to the east. Does the river current contribute to where we go, Natalie, or is that where we actually end up going? Good. Contributes to where we go, so we're going to make that 8 meters per second to the east. Now, this 850 meters, don't get thrown off by that. Okay, that's important later on, but we never draw a displacement vector in the same diagram as a velocity vector. If your vector diagram is velocity, it's got to be velocity. If it's displacement, that's okay, but it's got to be displacement for all the vectors. So let's not worry about that 850 meters right now. Let's draw the vector diagram here. We have one that's this way at 8 meters per second, and we have one that's this way at 25 meters per second. We could have just as easily drawn it like this, right? Is one better than the other? No, I don't think so. Okay, as long as they're drawn front to back, it's all good. All right. Looks like the river current is flowing this way to the east. So I'm going to draw in my river right now. Okay, there's my river. The river is 850 meters wide. Remember I said that's not forming part of your vector diagram, but I'm going to label it. In my resultant vector, or my dotted line vector, the velocity relative to the shore is going to be drawn from start to finish. We want to find that velocity relative to the shore right now, so let's find the value of r. Good news is it's pretty easy to find here. We're going to say r is equal to the square root of 8 squared plus 25 squared. And when we do that, we should get 26.25 meters per second, or 26 meters per second. The angle, always drawn at the start of the vector diagram, is going to be the inverse tan function of opposite over adjacent, 25 over 8. And when I do that, I end up getting 72 degrees. 72 degrees north of east. Had I drawn the diagram the other way, with the y-axis first, 25, then the 8, then I would have had a value of 18 degrees north of east. Question B requires a little bit of thought. Okay, this isn't straight from examples that we've done in class. It says, what's the time that it takes the ship to cross the river? Well, assuming this ship is traveling at a constant speed, and there's no reason to think that it's not, then the equation that we're going to use is a group A equation, V equals D over T. Back to this one now, back to group A, because it's a constant velocity. We want to find the value of T, so let's rearrange this. Delta T comes up by multiplying, V goes down by dividing, and then end up getting delta D over V. All right, good enough. The displacement that I have is 850 meters. It's the only displacement I have, right? Displacement across the river. What's the value of V? What's the value of V? Lots of you probably thought, 26 meters per second. Well, I bet, how many people were thinking, oh, 850 divided by 26? And you get an answer that's real close to the actual answer, right? But that's not right. I'm going to write that in for a second, but understand, don't write that down because it's not right. Take a look at this and tell me why that's not right. Why can't I use 26 meters per second there? Is that velocity that I just solved for wrong? Yes. The 26 meters per second is relative to the shore, so it's at an angle. The 850 meters is straight across. Here's the thing. The very first day of, not the very first day of class, the second day of class this semester, when we learned about velocity, we learned that if something moved to the right, the velocity was to the right. If the displacement was down, the velocity was down. If the displacement was to the east, the velocity was to the east. If the displacement is north across the river, then the velocity has to be north across the river. The displacement and the velocity have to be in the same direction. So I'm not going to use 26 meters per second along with 850. I'll use 25 meters per second along with the 850, because the 25 meters per second is in the same direction as the 850. Does that make some sense? Divide those two, we get 34 seconds. Now, you could do this a longer way and use the 26 meters per second. Okay, if you wanted to use the resultant vector here of 26 meters per second, you could do that if you have this displacement. Does that make sense? The displacement at the angle. And you could find that. Okay, given the angle, given the 850, you could find this. And then say whatever that displacement is divided by 26, it would still give you 34 seconds. But to me, that's a lot of extra work. If we have a displacement already along the y-axis, and we have a velocity along the y-axis, why not just use those? It's going to give us our right answer. And it's less work. All right, question C. How far downstream does the ship end when it reaches the other side? So in other words, the river current is going to the east there. Okay, the ship is going to travel downstream here. How far downstream? How far downstream does it end up going? It's traveling at a constant velocity still. And I want to find how far downstream it ends up going. So I want to find a displacement. But I want to find a displacement along the x-axis. I want to find this displacement, right? If I want to find the displacement along the x-axis, what velocity must I use? Let's go back to the picture. If I want to find the displacement this way, then what velocity do I have to use? 8 meters per second. Because remember, the velocity and the displacement have to be in the same direction. So, plug in 8 meters per second. If I want to find the horizontal displacement, I got to use the horizontal velocity. What time do I use? What time do I use? Yeah? 34? All right, wait a second here. This one, question B, I use the velocity and displacement along the vertical axis. In question C, I use the velocity and displacement along the horizontal axis. And I said back here that if you're using vertical displacement, you've got to use vertical velocity. I said here, if you're using horizontal displacement, you want horizontal velocity. You're saying I can use the time for horizontal and vertical at the same time? Why? Why can I use the same time here as I use here, but I can't use anything else between those two questions? Because time's a scalar. Right. Velocity and displacement have a direction. It's either x or it's y. But time's a scalar. I can put time in x or y. It doesn't really matter because there's no direction associated with the time that it took the boat to cross the river. 8 times 34 gives me 2.7 times 10 to the 2. 272 or 2.7 times 10 to the 2 meters. Is that good? Let's do another example now. This one says the pilot of an airplane wants to go directly north at a velocity of 500 kilometers per hour. So it's like the pilot leaves Calgary, wants to go to Edmonton at 500 kilometers per hour, but there's a wind blowing to the east of 85 kilometers per hour. So the wind is going to blow the pilot off course, right? We want to know where the pilot of the plane must aim or must head in order to go straight north. We want to go north, but we can't aim north because the wind's going to blow us off course. If we want to go north, then we got to aim somewhere else to compensate for the wind that's blowing to the east. Where do we have to aim? Okay, with what velocity and what angle do we have to aim at? All right, let's look at what we got here. The pilot of a plane wants to go directly north at 500 kilometers per hour. Now, where the pilot wants to go, does that contribute to the pilot's motion, to the plane's motion, or is that the plane's motion? Is that a contributing factor, in other words, a solid line vector, or is that a dotted line vector? Is that a result of a bunch of other factors? It's a dotted line vector, yeah. That's where the pilot goes. Let's assume the pilot is good enough when he's flying his plane or when she's flying her plane that the pilot ends up where he or she wants to go. Okay, let's assume that they're good enough to end up where they want to go. If they end up where they want to go, it's going to be the result of a couple of other factors. So that means that's going to be a dotted line vector. This is a little bit tricky, okay? We're drawing for the first time a resultant vector before we know what the solid line vectors are. Let's draw that down here. My resultant vector is north at 500 kilometers per hour. My dotted line vector, north at 500 kilometers per hour. There's a wind blowing to the east at 85 kilometers per hour. That's not where I'm going, right? Because I already know where I'm going. I'm going north. The wind to the east contributes to where I go, contributes to the overall velocity of this airplane. So we're going to draw that as a solid line vector like this. Now, we have to try to draw a right angle triangle vector diagram, this time without knowing what both solid lines are, but rather knowing what one solid line is and one dotted line is. So let's try that here now. Here's my 500. I'm going to draw, you know what, I'm going to change the color of this 85 just so it stands out a little bit more. So where am I going to draw that 85 kilometer per hour vector? I'm going to give you 4 options, and I want you guys to tell me which one of the 4 options might work here, okay? I can draw it position, well, I'm going to draw it position 1. Doesn't mean I can draw it there, okay? I want you to tell me if I can or not. Position 1, position 2, position 3, position 4. Clearly, I'm not going to draw it in all 4 places. I want one 85 kilometer per hour vector. But where am I going to draw it? Position 1, position 2, position 3, or position 4? Any ideas? Rosie, what's your idea? Okay, Rosie says position 2. Anybody else say position 2 or say something different here? I'll give you a hint. There's actually 2 places that I can draw it, 2 options here. So Rosie may be correct, she may be incorrect, but there's at least one more option, even if she's right. There's at least one more option. Yep. Position 4. Okay, so position 2, position 4. Anybody else? If they're both right, then there are no other options. Right? If they're wrong, then there are other options. Who says position 2 looks good? Uh-oh. Position 4. Okay, I mean, you could vote for both of them, right? Because they could both be right. Who says none of the above? Position 1 or position 3? What do you say? Position 1 or 3? Okay, I'm interested to hear why you said that. The lone wolf here who's saying position 1 or position 3. Yep. Yep. Okay, I think I get what you're saying there. You're right, by the way. It's position 1 or position 3. I'm going to choose to draw it at position 3, but position 1 would work as well. Let me give you a slightly more succinct reason for being position 3 or position 1 for that matter. The dotted line vector is our resultant. The dotted line vector must be drawn from start to finish. If I draw my solid line vector right here, then my dotted line vector is not drawn from start to finish. It's drawn from finish to something else. That make sense? Dotted line has to be start to finish. Okay, if I draw it up here at position 3, then my dotted line is drawn from something to finish. So it seems like it might work. Let's draw my other vector right here. This is the wind vector. This is what I want to find. It's not the resultant vector. I'm just going to call it V, the velocity of the wind. Or sorry, the velocity that I aim at. Logically think about this, okay? Logically think about it. If I want to go north and there's a wind to the east, I'm not going to aim like this. I'm not going to aim northeast, right? If I want to go north and there's a wind to the east, I want to aim somewhere in the north and west in order to compensate for that wind. I want to aim against the wind, not with the wind. Do you see how this is correct? My dotted line vector is drawn from start to finish. My 2 solid line vectors are drawn from front to back. Make sense? Here's the rule of thumb with this that I like to go by. Okay, in terms of, you know, not having to literally draw 4 diagrams to see which one works best. My rule of thumb is this. If you have a wind or a current or something like this, and you already have a dotted line vector, whatever vector you're given, draw it head to head. Okay, draw it front to front. Okay, that's what I did right here, right? I had the dotted line vector, I had a solid line vector, I drew it front to front. And then I was able to find the third vector, the other solid line vector, by just connecting the dots, basically. Now, we can find the value of v here pretty easily, right? Mathematically, this is no harder than other questions we've done. But remember, we're not finding the resultant this time. We're finding one of the solid line vectors, what contributes to the resultant. V is still going to be the square root of 85 squared plus 500 squared, because it's still the hypotenuse, even though it's not the resultant. And theta is still drawn at the beginning here, still the inverse tan function of 85 over 500, the opposite over the hypotenuse. See, this side of the room, okay, Emma's side of the room and over, let's get V, and then this side of the room and over, let's get the value of theta. So you guys are all getting theta, okay? 5.1 times 10 to the 2 should be two significant figures because of the 85, right? This is 3 digits, this is 2 digits, final answer should be 2 digits. And the angle should be somewhere over here. Fraser? 10 degrees? And that would be 10 degrees east of north because we're measuring it from the north axis, but it's east from the north axis. Right? So you want to fly a plane straight north. There's a wind to the east. Sorry, that's not east of north. What should that be? That's west of north, isn't it? You want to fly a plane straight north, but there's a wind to the east. What do you got to do? You got to aim kind of to the west, right? It's that example that I gave you yesterday in class, right, where you're driving. There's a Chinook, a strong Chinook wind blowing in from the west toward the east. You're driving your car straight north towards Calgary, but you get your steering wheel turned like this, right? The wind is going this way. You turn your steering wheel against the wind to compensate for the wind. Okay, the wind is going to the east here. You turn your steering wheel to the west, to the north and west to compensate for that. Good. You know, let's let's give you 6 and 7 right now. Okay, 6 and 7 right now, and then we'll do another example in a little bit. Oh, we won't do another example in a bit because of the time here. Let's do questions 6 and 7 on your worksheet right now, and then we'll worry about the other two later on, okay?